Welcome back. In the next several lectures, we're going to talk about Newton's method. Newton's method is incredibly powerful. As we're going to see, it is, in terms of the number of iterations required to gain a particular accuracy, much faster than gradient descent in the best cases of gradient descent, much faster than accelerated gradient descent. Where gradient descent enjoys linear convergence, Newton's method enjoys quadratic convergence. We're going to talk exactly about what that is and appreciate how much faster it is than gradient descent. Let's have a first view of what Newton's method is and how it compares to gradient descent. And in order to do that, I want to go back to how we motivated gradient descent in the first place. So in everything here, we're talking about minimizing a convex function. And as we'll see, Newton's method requires being able to take second derivatives. So in addition to assuming that f of x is convex, as we do throughout this entire class, we're going to assume that f of x also has first and second derivatives. We're going to have some additional assumptions on properties those first and second derivatives have to satisfy, but for now, don't be alarmed when you see second derivative, namely the Hessian, because we're just going to assume that we have this. We need it in order to be able to talk about Newton's method at all. So what was gradient descent? Gradient descent, one way to motivate it is to say, I don't know how to minimize f of x, that's a hard problem, so instead, let's make a linear approximation to f and minimize that. So the idea was, let's say that f of x is roughly equal to f of x plus the gradient of f at x times the direction d. And let's now, this is a linear function. And linear functions we know how to minimize. So gradient descent minimizes, chooses a step d, a direction d, which minimizes this linear function. Of course, as we've talked about, if we were actually going to minimize it all the way, we wouldn't want to do just a linear function because linear functions don't have a minimum. They'll just go off to minus infinity. So gradient descent minimizes this linear function plus a simple quadratic term just to keep us close, but a quadratic term that requires no information about the function. It just says choose a d, don't make d too big. And this eta that I put is the step size. And in the best case, the convergence rate that we've derived for gradient descent is as follows. If f is beta smooth, remember this means that the gradients are Lipschitz, and alpha strongly convex, this means that there is a quadratic lower bound to our function. And as we've shown many times, beta smooth is equivalent to having a quadratic upper bound. Then gradient descent has convergence order log 1 over epsilon. Actually, let me be a little bit more. I'm hiding a few constants that in our other analysis have been important. These are how well-conditioned or ill-conditioned the function is. So let me write that. Order beta over alpha times log 1 over epsilon. So we see that we have this log 1 over epsilon. This is called linear convergence. And it's linear convergence. It's called linear because if you plot it on a scale where you have the number of iterations versus the logarithm of the error, then you would see something like a straight line. Another way to think about linear convergence intuitively is that one additional iteration gets me one more digit of accuracy. Okay, well, if we were so successful at minimizing a linear approximation, and we saw that it has a great convergence rate, a natural idea is let's keep using our friend the Taylor series. Let's formulate a quadratic approximation and then minimize that. And this is exactly the idea behind Newton's method. So it says, let's approximate f of x plus d, not just by the linear approximation, which we use for gradient descent, just what we wrote on the previous slide, but let's also add the second order Taylor, the second term in the Taylor series. That's 1/2 times d transpose. And what goes here is the second derivative. But f is a function from n variables. Let me write that. So f is a function from n variables. Sometimes we've used d variables, but I'm using here d for the dimension vector, so I don't want to overload it, to r. And therefore that means that its derivative, its gradient, is going to be a vector in n dimensions, and therefore its second derivative is going to be a matrix that's n by n, and this is called the Hessian. And it's denoted in this way, times d. So just to refresh your memory, this is an n by n matrix, and the ij element of this n by n matrix is the second derivative, partial derivative of f, with respect to xi and xj, and it's symmetric. And we also know that if f is strongly convex and smooth, then the largest eigenvalue of this matrix is upper bounded by the smoothness, and the smallest eigenvalue is lower bounded by the strong convexity parameter. So this is the quadratic approximation. And the advantage of a quadratic approximation, just like a linear approximation, is that we can also solve it. So we'll talk about that in the next slide. The convergence rate is, again, much faster. The convergence rate is order log 1 over epsilon. Okay, so this is dramatically faster than linear convergence rate, which is just log 1 over epsilon, and this is called quadratic convergence. One intuitive way to think about quadratic convergence versus linear convergence, I mentioned that linear convergence, you can think of it as one iteration gives you one digit of accuracy. For quadratic convergence, one iteration doubles the number of digits of accuracy that you have. So it is really dramatically faster. So if Newton's method is so much faster than gradient descent, then why would we ever use it? In order to answer this, why would we ever use gradient descent? Why have we spent so much time talking about gradient descent and its various different forms? So in order to answer that question, like many things we've discussed in this sequence of lectures, there's not always a clear answer. It's not that Newton is always better than gradient descent or gradient descent is always better than Newton. We need to understand what the different trade-offs are. So in order to understand those trade-offs, I'm going to write down Newton's algorithm, and I'm going to write down the gradient descent algorithm. So for Newton, let's go back to what we just wrote on the previous page. So the Newton update forms a quadratic approximation, just copying exactly what I wrote on the previous slide. This is f of x plus the gradient of f of x transpose the new direction d that we move in, plus 1/2 d transpose this matrix, this Hessian matrix, times d. This is a quadratic. This is a convex quadratic function in what variable? D, right? Because x is fixed. I'm doing a quadratic approximation of f around the point x. It's d that varies. So I want to regard the right-hand side as a function of d, and I want to find the best d. I want to find the d that minimizes the right-hand side. This is just a convex quadratic. I can solve directly. Let's take the derivative, set it equal to 0. take the derivative with respect to d, set equal to 0, and solve for d. We've done this quite a number of times in this course. And doing this, we get gradient of f of x plus the Hessian of f of x dot product with d, or times d, matrix vector product. This is equal to 0. And therefore, d is equal to minus the inverse Hessian, I'm doing two steps at once here, times the gradient. How did I get that? I moved the gradient over onto the other side. I multiplied both sides on the left by the negative, by the inverse of the Hessian. Okay, so that means that my Newton step, xt plus 1, is equal to xt minus, or plus d. So let's write it more clearly, xt plus d, which is equal to xt minus the inverse Hessian times the gradient. And let's compare that to our old friend gradient descent. Xt plus 1 is equal to xt minus my step size times the gradient of f of x t. I forgot to put the xt's there for Newton's method. So let's compare these two. In the previous two slides, I told you what their convergence rates were, but let's compare them from a computational perspective. How much compute does it take? Now, one thing that we've generally not been talking about in this series of lectures is how long it takes us to compute the gradient. Now, one notable exception is we did talk about that quite a bit when we were talking about stochastic gradient descent methods. But in general, we have not been talking about how long it takes to compute the gradient of f. And in some settings, this is quite important. In neural networks, for example, the gradient computation itself is very expensive. Whereas in linear models and generalized linear models, it's actually quite straightforward to compute the gradient, computationally straightforward. So I'm going to continue to ignore that and just look at the other computations that are required. So gradient descent, what does it require in order to compute one step? If someone hands you the gradient, you need to just do a vector addition. You need to take the vector xt and add it to the vector minus gradient of f of xt. So this just requires, so computationally, gradient descent requires just vector addition. And this takes order n time. I need to add two vectors of length n. This takes order n time. What about Newton, on the other hand? Again, ignoring the potentially very important question of how did I actually compute this matrix of n squared second derivatives? Let's ignore that for now. I still need to invert an n by n matrix. If someone just gives me the Hessian, I still need to invert it. And then I need to multiply that matrix by a vector. And finally, I need to do a vector addition. So it's the first term of inversion which dominates those three. So in a big O analysis, it's really only the first one that would matter. That's about order n cubed time. The matrix vector multiplication would be order n squared. And then finally, the vector addition would be order n. But the dominant term here comes from matrix inversion. Now, there are faster algorithms for matrix multiplication and matrix inversion, but I'm just going to give a naive algorithm would take about order n cubed time. Order n cubed for any medium to large size problem is really astronomically larger than order n. So this gives us our answer of why would we ever use gradient descent? Shouldn't we just always use Newton if it's so much faster? So let's put these numbers all together, and we see that in order to get accuracy epsilon, gradient descent requires, again, I'm simplifying quite a bit because I'm not counting the amount of effort it takes, computational effort it takes to compute a gradient or even to compute a Hessian. But even leaving that aside, we still get a good picture of what's going on, what's the story. So gradient descent requires order n, that's the number of computations I need for one step, and the number of steps I need to get order epsilon, beta over epsilon error, beta over alpha times log 1 over epsilon, versus Newton, which is order n cubed times log 1 over epsilon. You can see that neither one of these functions uniformly dominates the other. If I care about an absolutely tiny, tiny epsilon, then no matter what n is, then even for a big n, the log 1 over epsilon is going to be what wins. But as n grows, then log has to be really much, much, much smaller than log 1 over epsilon. And log 1 over epsilon is already pretty small. So in other words, for smaller n, if you have a smaller problem and you really care about very, very high accuracy, Newton is your algorithm. For a large problem where you may not be so intent on absolutely tiny epsilon, then you need gradient descent. So it's important to know these issues because it's ultimately up to you, knowing your application, knowing your computational resources, to decide what is the best optimization algorithm to use. So we just derived the Newton direction in the previous slide. I'm going to write that down again. So the Newton direction we get by solving this approximation, f of x plus d is equal to f of x plus gradient of f of x dot product with d plus 1/2 d transpose Hessian of f times d. And d subscript n for Newton, as we just derived, is equal to minus the Hessian of f inverse times the gradient of f of x. And so Newton's method tells us that xt plus 1 is equal to xt minus d. Okay, you might correctly say, well, gradient descent also had another parameter which I don't see here. Gradient descent always had a step size, and here there seems to be no step size. So in fact, we're going to need a step size, and this is going to be a big part of our discussion when we talk about Newton's method. So let's turn to that. So there are two versions of Newton's. One is the one we just wrote, and that's called undamped Newton's method, and the other one is called damped Newton method. So damped Newton's method, xt plus 1 is equal to xt minus a step size that will be less than 1 times the Hessian inverse times the gradient of f of xt. Again, note the computational requirements are exactly the same. And undamped, xt plus 1 is just what we wrote on the previous two slides. The Hessian inverse times the gradient of f of xt. What we need to understand is why would we use damped or why would we use undamped? So properly, Newton's method operates in two phases. Phase 1 is when we're not very close, and we're going to use damped Newton's method. When not very close to the optimal solution, we use damped Newton. And in phase 2, when we're very close, we use undamped. And what we're going to see is that after a finite number of uses of phase one, we're guaranteed to enter the region where we can move into phase two. So we're always going to have a finite number of rounds of damped Newton, and then we're going to get into this undamped phase, and it's here where we get the region of quadratic convergence. So this is a story for Newton's method, the basic outline. We're going to stop here, and in the next lecture, we're going to talk about a different view of Newton's method, different origin. We'll pick it up then.